Fast and robust eye tracking is important across many fields, from virtual reality, where it's used for interactive and efficient rendering, to surgery, where it's used to ensure people keep their eyes still during LASIK. Commercial, mobile eye tracking solutions are limited to 120 to 200 Hz and accuracies of about 1 degree of visual angle. Desk-mounted systems like the iLink 1000 are considered the gold standard, providing about 1000 Hz and half a degree of visual angle using large, power-hungry, expensive components. No small, fast, and accurate system exists. The eye has some of the fastest moving muscles in the human body, contracting in less than 10 milliseconds, so speed is critical for eye trackers. To properly measure the fastest, most subtle movements of the eye, like microsaccades, we have to sample many thousands of times per second. However, it would be nearly impossible to build a fast, accurate, and portable system with traditional cameras. At 10,000 Hz, even a low-resolution sensor would produce 7.2 gigabits of data per second, 50% more than the maximum throughput of USB 3.0. This would require too much power and memory for buffering. Our work builds on the key insight that the data captured by near-eye cameras is sparse. Visualizing the temporal gradient of a captured video sequence shows that only a subset of the pixels actually change in successive frames. To exploit this characteristic, we propose an eye tracking system based on event cameras. Instead of frames, these cameras produce a stream of events indicating the XY location and intensity changes. In our eye tracking scenario, the event camera only reports information when the eye moves and can stream events, millions of times per second per pixel. Our system uses a sensor that reports both synchronously sampled frames and asynchronous events as seen here. The events report eye motion thousands of times in between each frame. Our algorithm uses both frames and events as input. We then use an algorithm detailed in the paper to update a pupil model every one or few events. With the pupil fitted, we regress a gaze vector in real time. Please refer to the paper for additional details. Here is a visualization of our event-based pupil fitting procedure. As seen here, the proposed method produces an almost continuous fit of the pupil motion between the frames. Here are some results, filmed with a subject following a mouse pointer with their eyes while using our event-based eye tracker. Here's another perspective of the user. We collected a dataset comprising frames and events of 24 subjects with different eye motions. This dataset will be made public. We also extensively evaluate our system and demonstrate accuracy that is comparable to the best commercial eye trackers, with update rates that are 1 or 2 orders of magnitude faster. In summary, our work introduces event-based eye tracking to overcome long-standing challenges in this domain.